Hey guys, in this video what we're going to look at is trying to dig into the differences between Schrodinger's model of the atom and Bohr's model of the atom. And we're really going to start pulling apart how we start changing Bohr's rings or shells into Schrodinger's orbitals. And we're going to use some terminology including sublevels and orbitals and electrons as we start making this transition from our standard looking ring model of the atom into Bohr's idea of putting electrons into orbitals. So first and foremost, we're not going to abandon Bohr's idea of energy levels. We're just going to change it a little bit so that instead of talking about specific rings or specific lines where we're going to place electrons, we're going to start putting electrons more into zones. So for now, those zones we're going to start dividing up into sublevels. And each energy level contains a specific number of sublevels. So here on this diagram, were this to be Bohr, this would be ring number 1 right here outside the nucleus. So what I'm going to redefine that as is energy level number 1 that kind of exists between the nucleus and Bohr's original ring. And I'm going to give it one sublevel that I'll mark in green. As we move away from the nucleus, what you're going to find is that there's more space, right? This is a bigger space for more sublevels. And even though this is just a small slice of what would be a mostly spherical atom, this is going to try and be representative of what we're going to be able to see in terms of number of sublevels. So as we move up, again, instead of ring number 2, we're going to have energy level number 2. And there's going to be space for that green sublevel again. But there's also still a lot more room in that sublevel. So we're going to be, in that energy level. So we're going to be able to give it a second sublevel that I'm going to put in purple. And you'll notice that this is a little bit larger. We're going to move up again and again because we're not dealing with Bohr anymore, not ring number 3, but energy level number 3. We have space for even more sublevels. We'll go and we'll start with our green guy. And we'll add in our purple, but there should still be some room left for another sublevel. And we find that in atoms, this tends to be true as well. So I'm going to add in a third sublevel in energy level number 3. And I'll add that guy in blue. And again, notice that the blue sublevel is even a little bit bigger than our purple one. And as you can imagine, if we move up one energy level more, up into energy level number 4, there's even more room for some of Schrodinger's sublevels. So there's space for that green one. There's space for the purple. There's space for the blue. And there's still even more room for another sublevel as we move away from the nucleus. And I'll include a fourth sublevel in orange. And if this were an ideal world, that orange sublevel would again be even larger than our blue one. And yes, we could continue moving up into energy level number 5, number 6, number 7, and so on. But as we move up, what we'll find is that since there's only 118 elements that have been discovered, we only have observed 4 different types of sublevels that I've represented initially here with colors, but we'll start to refer to by their more formal names, which really aren't that much more complicated. We refer to sublevels using little letters. So this green sublevel that appears in every single energy level, we call the S sublevel. So here we've got an S, an S, and an S sublevel. The second sublevel that we know exists is sublevel P, and I'll mark that in my purple. And you'll notice that that appears in 3 out of our 4 energy levels in our diagram. The D sublevel is another name for this sublevel that appears in energy levels 3 and 4. And F was what seems to be the least common in our diagram, is our fourth and final sublevel that we've observed in atoms. So yes, it is true that as we move away from the nucleus, we get more and more space for more and more sublevels. They do exist, but some of them just aren't going to be filled because we just plain run out of electrons to fill them with. And we'll see that as we move forward through this lesson over the course of the 3 videos. So as it turns out, each of these different sublevels has a different size and shape in the atom. The S sublevel is the smallest, and so it's going to fit not as many orbitals as our slightly larger P sublevel. Notice I threw the word orbital in there. Remember from class, orbital is just a space where electrons are most likely to be found. So sublevels are kind of like our zone, and then orbitals we can find within a sublevel, and that's where we're going to try and cram our electrons. Sometimes it kind of works to think of it as an analogy, and that's what we'll get into in just a second. But for now, what's noteworthy is this idea that each different sublevel holds a different number of orbitals, simply because they're different sizes and different shapes. And each orbital within each sublevel can hold 2 electrons and 2 electrons only. So if we're limited in our number of orbitals, we're limited in our number of electrons, and we're going to see how that kind of plays out. If you want to dive into analogies, we can kind of think of this scenario as a weird looking hotel, all right? Your energy level is going to tell you what floor you're on. Are you on floor 1, real close to the ground, or are you moving way up in levels? Your orbital is going to be dealt with later, because first I want to talk about sublevels. So once you've figured out what floor you're on, you want to know what wing of the hotel you need to go to. Do you need to stay right by the elevators? Do you need to go down the hall a little bit? Do you need to turn right? Or do you need to go the way back of the hotel? So your sublevel kind of distinguishes where on the floor you are. And your orbitals are kind of like rooms in those wings, right? Each wing has its space for a different number of rooms, and it's in the rooms that you're going to find people, aka electrons, all right? So as we move through this hotel, we can go up in energy, we can look in different wings of the hotel that are going to be slightly easier or more difficult to get to, and each wing is going to have a number of different rooms where we're going to find our electrons. So let's break that down just a second, all right? You'll notice in our S sublevel, the smallest, we only have space for 1 orbital. And because each orbital can hold up to 2 electrons, our S sublevel can hold up to 2 total electrons. And that's in each S sublevel. Our P sublevel is a little bit bigger, so it can hold more orbitals. More orbitals means more possible electrons. P sublevels can hold up to 3 orbitals. 3 times 2 is 6, so that means each P sublevel can hold a total of 6 electrons. You're going to start noticing an additive effect here. Notice that in energy level 1, we're maxed out at 2 electrons. In energy level 2, we've got space for 2 plus 6, or 8 electrons. Hopefully these numbers will start looking familiar, thinking back to Bohr's limits. The D sublevel has space for 5 orbitals, or 5 rooms in its wing. 5 times 2 gives us a total of 10 maximum electrons in any D sublevel. So again, looking at that additive effect, in our 3rd energy level, we now have room for 2 plus 6 plus 10 is 18 electrons. And as you can imagine, well, maybe not, your F sublevel has space for even more orbitals, 7 of them. And 7 times 2 gives you 14 possible electrons that we could find in the F sublevel. Looking at that math, we're now up to 32. So we're going to start making those ties and transitions to the Bohr model and then applying it to the periodic table and the way it's structured and the way we use it. And that's going to be the topic of the next video. But for now, pause this video, go back into your mini lesson notes, make sure you have everything written down and you're clear on this idea of S, P, D, and F and what I mean when I use those letters.